Side one, we're going to talk about, so we're in the sequences piece, and we're just going to talk about some terminology. With sequences and series, terminology is pretty important. So let's talk about the important pieces of terminology and then the pieces that are maybe a little less important. The first thing is that we want to understand what it means for a sequence to be increasing or decreasing. Those are the most important two words up there. And then the next one after that is bounded. So if we think of a sequence as a function, which is the best way to think of a sequence is a function, and the domain of that sequence is the positive integers. So a sub 1, a sub 2, a sub 3. So we have a sequence that is a function. So whenever you're thinking about a sequence, that's what I want you to think about in your head. Think of it as a function. Visualize a graph with a bunch of dots on it. That's what you should be thinking about with the sequence. And of course, when you're thinking about that sequence, the domain is the positive integers, so there's an equal space between those dots horizontally. Right? You're going 1 unit in your index. So a sequence is increasing if the terms get bigger. So as you move from left to right through the sequence, the terms are getting larger in value. Then it's increasing. The sequence is decreasing if the terms are going down as you move from left to right through the sequence. So those are the most important two, and those are the two we're going to focus on a lot. Now in math, you have already seen that mathematicians love to be as general as possible. And so most theorems will take the most general possible assumption imaginable that will give you a good conclusion. When you look at these two sequences down here, this black sequence is increasing, this red sequence is decreasing. That's really, those are comfortable words. We can sort of visualize those really easily. But in practice, that's usually totally fine. To create one of these other two types of sequences that are non-increasing and non-decreasing, it's a little hard. Like the functions, we usually are going to define our sequences with functions, and the functions that we know are either typically increasing or decreasing. To create a function that goes flat and then continues up, the only way we've ever been able to do that is with a piecewise function. So the connected idea with increasing is non-decreasing. And in your mind, non-decreasing means not going down. So it's either staying the same or going up. So if you look at this example here, it's trending up, but it's possible to have some flat spots. So this is the generalization of increasing. All right, and then for decreasing, same idea. Non-increasing means not going up, so it can stay flat or go down. So it's trending down, but it can have flat spots. But again, in practice, creating a non-decreasing or non-increasing is very hard. So if we're just looking at functions like you're used to from Calc 1 and pre-calculus, they're either going to be increasing or decreasing. And if they're oscillating, obviously there's something else going on. So if a sequence is non-increasing or non-decreasing, and in your mind, it's totally fine to replace those with decreasing and increasing. So if you have a decreasing or increasing function, we call that monotonic. Monotonic means that there's never any oscillation. If it's trending up, it could never then take a step down. If it's trending down, it could never take a step up. So monotonic means that it's either trending up or trending down, but never a blip, never a wobble, never an oscillation. All right, and then Sequences can be either bounded above or bounded below. The sequence that's bounded above means there's a cap, that the sequence values never go through that number. Bounded below, there's a floor. So we've got a floor and a ceiling. Possibly, depending on the sequence. And a sequence that has both a floor and a ceiling, we call that sequence just bounded. So a sequence could be bounded above but not below. It could be bounded below but not above. But if it's bounded in both directions, then we say that sequence is bounded. So, for example, this red sequence is decreasing. And if we look at that, does that sequence have a lower bound? Is it bounded below? And the answer is yes, it's bounded below. It's never going to go below a certain value, and that value happens to be 1. If you look at the limit of the sequence, as n goes to infinity, 1 plus 1 over n goes to 1. This value is always bigger than 1, but it's never equal to 1, so 1 would act as a lower bound. Similarly, on this one, 1 would act as an upper bound. This number in here, a sub n, is always a little less than 1. As n gets bigger, you're subtracting a smaller amount from 1, but it is always less than 1, so 1 would act as an upper bound. This red sequence is bounded below, but it's also bounded above, right? There's no number in the sequence that's above 2, nor will there ever be. So this one is bounded above and below, so we would say it's bounded. This black sequence is bounded above by 1, it's bounded below by 0. There's no value less than 0. So both of those are bounded sequences. And you can imagine an unbounded sequence. It just goes on forever, like something like 2 to the n. It's just going to keep going up forever. All right, so let's look at a couple of examples. Let's see, where are we? So let's look at this specific type of sequence, probably the most important type of sequence that we're going to see. This is called the geometric sequence. And the geometric sequence is, it looks like an exponential. So n goes off to infinity, and it's on a number. So r is some number. We raise it to the nth power. That's called geometric. And you already sort of know this. This should be intuitive. If you take a number, we talked about it on Tuesday actually, if you take a number that's less than 1 in magnitude, and you multiply it by itself repeatedly, that's going to approach 0. A half times a half is a fourth times a half is an eighth. It gets smaller and smaller and smaller, approaching 0. Never gets to 0, but it approaches 0. So it's limited 0. If you plug in a 1 for the r, of course the limit is 1, because 1 times 1 times 1 times 1 continues to be 1. If you plug in a number that has a magnitude greater than 1, so 2, negative 2, anything that's further than 1 from the origin, magnitude bigger than 1, that limit will not exist because it's going to go to positive infinity if r is bigger than 1. 2 times 2 times 2 times 2 repeatedly, that's going to go to infinity. Now if you choose something that's less than 1, like say negative 3, it's just going to oscillate and go off. All you could say is that the limit does not exist because there's going to be positive values that get arbitrarily large, and there's going to be negative values that get arbitrarily negative, more and more negative. So here are some pictures. So here is 1/2 to the n. As you would expect, the terms in the sequence are approaching 0 because you're multiplying 1/2 by itself repeatedly. So that is a picture of a decreasing sequence that is bounded below by 0. Here is a picture of negative 1/2 to the n. So negative 1/2 to the n is still going to have a limit of 0, but it will have some positive values. Every other term will be positive, every other term will be negative. But they're going to come together towards 0. So it will still have a limit of 0, but it's going to oscillate as it approaches 0. And then this one, we have an r value a little bit bigger than 1, and as soon as that r value gets a little bit bigger than 1, it's going to diverge. So this one is a positive 1.1, so As n goes to infinity, it's just going to steadily go towards positive infinity. Down here, I have 1.1. I have negative, this is negative 1.1 to the n. So it's going to oscillate. Parts of it will go towards positive infinity, parts will go towards negative infinity. So the limit, the only thing we can say about the limit is that it does not exist. Now, it is true, so this one does not exist. The limit does not exist. This one does not exist, but you can be descriptive about how it doesn't exist. It doesn't exist because the numbers are going towards plus infinity. It's true that this does not exist. The limit only exists if there's a single number that is getting closer and closer to. If we don't have a number that the terms are getting closer and closer to, the limit does not exist. But when we can, if we can add a descriptive, something that's more descriptive than just it does not exist, then we do it. So here we can be more descriptive. That limit doesn't exist, and it doesn't exist because the terms are going to infinity. Whereas this, they're oscillating, so we can't really, we can't be as descriptive.
Can you scroll it real quick?
Yeah.
A little bit more. Okay.
And so this one, the limit is 0, and this one is the limit is also 0. This one is decreasing towards 0. This one is oscillating towards 0. But both limits will be 0 there. Both will be 0. Now in Calc 1, you also had this theorem called the squeeze theorem for functions. You had it for functions in Calc 1 when you were finding limits. And it's the same idea. So in Calc 2, when we're talking about sequences, we've got 3 sequences. And the B sequence is trapped in between the A and the C sequence. So the B sequence is the sequence of black dots there. And if for every n, that B term is trapped between an A term and a C term, so it's in between. So if we look at any particular n, we see that the black dots equal to or in between, but not outside of. So we've got less than or equal to's. So it's trapped in between. If both of those outer sequences, the A sub n, the lower sequence, and C sub n, the upper sequence, if they have the same limit, then the sequence that's trapped in between must converge to that same exact limit value of L. No choice. So we call it the squeeze theorem. So in practice, when we're using the squeeze theorem, here are a couple of examples. And you typically need a function that is bounded in order for the squeeze theorem to work. So in this example, if we look at that function that we see, arctangent, we know that arctangent is always a number that's in between pi over 2 and negative pi over 2. It's never equal to. But you could put this in here. This is also true if you put equal to's in there, right? It's still true. Even though it is strictly less than, it's a true statement that if you change it to a less than or equal to, that's still true. So that's a true statement. And now what we do is divide everything by n. So we start by grabbing the bounded function, write down its bounds, and now we're going to try to create this inverse tangent of n over n by dividing everything by n now. So we're trying to create in the middle whatever the sequence term is. And that's also true. N is a positive number. And if you divide an inequality by a positive number, that doesn't reverse the inequality symbols. Everything is still true. If you have an inequality and you divide by a positive number, that inequality still holds, as long as that number is positive. Now we can take the limit across the board. So we can take the limit on the left, negative pi over 2 divided by n, as n goes to infinity. We can take the limit in the middle as n goes to infinity. And so this is the one we're trying to calculate. And then we take the limit of the right-hand side. And so as we take the limit across the board, what do we see about the right side and the left side here? Do those approach something we know? 0. All right, if you have a constant divided by a denominator that's getting arbitrarily large, those both go to 0. And so then we can draw our conclusion. So therefore, the limit as n goes to infinity of the thing in the middle must be 0. So we proved that this is true with the squeeze theorem. Conceptually, you're thinking about the numerator is bounded. If we have a numerator that's bounded and the denominator is getting bigger without bound, then those fractions have to go to 0. If the numerator is bounded. If the numerator is also going to infinity, then we have to do some L'Hopital rule stuff. But if the numerator is bounded and the denominator is getting infinitely large, then the fractions are going to get close to 0. They're going to approach 0. So same idea here. We look at our function inside, and that function is bounded. And so intuitively, when you look at that, you should say, oh yeah, the limit's got to be 0. The top is never bigger than 1 or less than -1. It's trapped in between -1 and 1. But the denominator is getting infinitely large. Yeah, those fractions are going to go to 0. But that's not proving it. That's just your intuition. And so to prove it, you do this kind of thing. You say, okay, well, let's start with our bounded function. That's a true statement. We know that from college algebra trig, pre-calc, whatever you took. And then we divide everything by n. And that's true. If you divide an inequality by a positive number, the inequality holds. And then we go ahead and take the limit of all 3 pieces. We take the limit across the board here. And when we take that limit, we see that on the edges, on the left side and on the right side, we have limit values of 0 once again. So both the left side and the right side, these are going to go to 0. And so that tells us then that the middle must also go to 0. So the limit of cosine n over n is 0. So that's the squeeze theorem. So the squeeze theorem proves this idea that as long as the numerator is bounded, if the denominator is going to infinity, the limit is 0. So we just verify that with the squeeze theorem. That is the power of the squeeze theorem. It proves that. Let's take a look at a really important theorem. So this theorem, the bounded monotonic sequences converge. So if you have a sequence that's monotonic, so that means it's either trending up or trending down, and it's bounded, it must converge. Now, every example they're going to show us is not with a true non-decreasing and a true non-increasing, because those are so hard to create. This one's really increasing, this one's really decreasing. So in your mind, when you see non-decreasing, think not going down, that means going up. So you can convert that to increasing. It's totally fine to think of this as increasing, totally fine to think of that as decreasing, because it's such an anomaly to actually create something that has flat spots. So think in your mind, if a sequence is increasing and it's got a ceiling, it must have a limit. And if a sequence is decreasing, there has to be a floor. If there is a floor, it has to have a limit. So if you have a decreasing sequence and there is a floor, there's going to be a limit. So that's what these pictures show. Now, one important thing to understand is that there's an infinite number of bounds if there is a bound. This number right here is an upper bound. This number right there is an upper bound. This number right here is a lower bound. That's a lower bound. That's a lower bound. So if a sequence is bounded below, it's bounded below by an infinite number of numbers. Getting the sequence bound that is the tightest, the one that's closest, that one is the limit. So the limit of this decreasing sequence is n, and that n is going to be the largest of all the possible lower bounds. Similarly here, where we have this increasing sequence, there's an infinite number of upper bounds. The least of those upper bounds is the one that's going to be the limit of that sequence. So, but the bottom line is, if it is bounded and it is monotonic, you have to have a limit. You know there's a limit. You know that the limit exists. So that's very helpful. Going down the road, we'll see where that's helpful as we get into some other stuff. Now there's a lot of weird functions in math. There's a lot of weird functions. Two of them are on this slide. One is the factorial function, and one is the power tower. And if you have not seen the factorial function is a product all the way down to 3, 2, 1. It's a product. So this product is what n factorial means. If you've had stats, you've seen this before. So for example, 5 factorial is 5 times 4 times 3 times 2 times 1, whatever that happens to be equal to. 10 factorial, same idea. You're just doing 10 times 9 times 8 times 7, all the way down to 3, 2, 1. So that's what factorial is. Our definition of factorial right now is that it's for positive integers. Positive integers. That's how you form factorial. If you've had a stats class or a probability class, you'll see factorials all over the place, because they're super useful when you're trying to predict probabilities. All right, and then there is the power tower. The power tower looks something like that if you put in numbers, and it is, when you substitute a number in, it is what you think it is. But that thing is not exponential, and it's not a polynomial. Polynomials, the variable is down in the base and the exponent's a number. For an exponential, the variable's up in the exponent position and the base is a number. All right, so not a polynomial, not an exponential. Power tower is neither of those. So, both of these are discrete. Right? N factorial is a number. We cannot take the derivative of a discrete function. So we cannot use L'Hopital's rule if we have a factorial or if we have a power tower. We can't use L'Hopital's rule, especially for that one, the factorial. You may suspect that that this may be a continuous function if you graph it. But we don't know how to take the derivative of either of those things, even if it were possible. We don't know how to do it. So, what this table is telling us is that if you can't use L'Hopital's rule, if you have functions that you can't differentiate, then we're going to use the growth chart as kind of a cop-out and not do the math. We're just going to say, oh, well, we know from this growth chart, it can be shown that the power tower grows the fastest of all these functions. And so I'll talk about what that means in a moment. Now, when you look at this, they have got 7 different combinations here. You should just break it down in your mind into these 5 categories. These 5 categories are plenty. This thing here where they start mixing functions and adding exponents and things, that's more complicated than you really need. You just sort of have to have this understanding that logarithmic functions grow the slowest, right? You're imagining sort of a bird wing looking thing. This grows the slowest. Polynomials grow the next fastest. And you all know exponentials grow faster than a polynomial grows. So these three should be really familiar already. And then at this stage, you just have to accept that factorials grow faster than exponentials and power towers grow faster than the factorials. So that's going to be our order. So when we look at this thing right here, and we try to take the limit of this, we have an indeterminate form here. Right? This is indeterminate. Both the numerator and the denominator are going to infinity. So up until this moment, if you had infinity over infinity as an indeterminate form and you were trying to take a limit at infinity, you would just use L'Hopital's rule and do a bunch of math and then reevaluate. We can't do that math in this class. We can't take those derivatives. So what we do is use the fact that this growth rate chart tells us that the power towers grow fastest. So if power towers grow faster than factorials, what's that limit have to be? 0. Has to be 0. All right, so this is the one case in calc classes where we're actually not going to do the math. If you can do the math, you do it. But if you can't, this is one of those cases where we just wave our hand and say, okay, we know power towers grow the fastest. But we don't even really know that. You're taking it on face value. Taking it on faith. Okay, so this one. Same idea here. When we look at the limit as n goes to infinity here, okay, it's an indeterminate form. We have the infinity over infinity situation going on. And you actually could do some math here. Those are both differentiable. You could take the derivative of the top, which is a polynomial, and the bottom, which is an exponential. But how many times would you have to differentiate this to get somewhere? 1,000 times? So when it's completely impractical or impossible, we just use growth rates. So this one here, exponential, grows faster than polynomial. It doesn't matter how big that power is. This power could be 10 million. This exponential will overtake it at some point, where this is exponential growth, not exponential decay. So the b is bigger than 1 for the exponential expression here. So it's an exponential growth. So this will overtake that. Even if you look on your calculator, it's going to take a long time. You know, x to the 1,000 or n to the 1,000 is growing wicked fast. But the exponential eventually will overtake it when you go far enough out in the ends. So again, this one is impractical. It is possible, but we're not going to differentiate 1,000 times. So this will also be 0, because exponentials grow faster than polynomials. As long as that exponential is exponential growth. So the base is bigger than 1. Bigger than 1. So this could be 1.1 to the n, and that could be n to the 5 billion. Limit's still 0. You have to go way, 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 way out to the moon. So in Calc 1, you had the formal definition of a limit of a function. In Calc 2, we have a formal definition of the limit of a sequence. And it's the same gist. So the idea, if we look at the picture, the sequence of black dots, that's our function. Sequence is a function. It's a function of the positive integers, typically. And for a sequence to have a limit, it just means that the terms are getting arbitrarily close to some number. Infinitesimally close. Whatever you want to say. Arbitrarily close is how we usually describe it. And so that means that when you think about this first part in the limit definition, a sub n minus l, that's representing this difference right here. Right? So if I look at, say, this sequence value right there, L is a horizontal line going across, and that distance, a sub n minus L, is the distance between the sequence value and that potential limit. And so all this says is that if the sequence value and the limit are close, like epsilon's a tiny number, so this just says they're close. This says that the sequence value and this number L are going to be super close whenever you go far enough out in the tail. And if that's true for every positive epsilon, then the limit exists. So it's a ratcheting type of concept. We provide epsilon. We say, hey, what if epsilon is 0.1? If your sequence converges, then you can go far enough out to find this capital N so that the rest of the sequence, which we usually refer to as the tail of the sequence is going to be trapped in this little epsilon tunnel here. And if that's true for every epsilon, if you shrink it down to 1/10, shrink it down to 1/100th, if you can go far enough out into the tail, all the way down there, so that the rest of it is in between, it's less than epsilon away, all the terms are less than epsilon from this horizontal line L, and L is just coming through like that, then the limit exists. So in your mind, you're just sort of thinking of this ratchet thing. You're imagining the dots getting arbitrarily close, infinitesimally close, however you want to think about it, just getting super tight on L. And so the limit will exist if this is true, no matter how small epsilon is. Then the limit exists. And of course you write it like that, like we've been writing it. So formal definition of a limit. We won't do any epsilons in here. We're not going to find, the capital N for a particular epsilon. You did a little bit of that in Calc 1, and you do it again later in some other classes. Not in here. It's kind of a pain. Okay, so we are going to visit recursion a little bit more. When you look at this recursive sequence, we want to know whether it converges or diverges. Now, if we look at the instructions here, it says that they're monotonic and bounded. Do you agree? When you look at this sequence, before you even look at values for the sequence, do you agree that it's monotonic? So that means either trending up or trending down. For our purposes, increasing or decreasing. So if we look at our first value, we're plugging in 2. So we have a 2 right there. And then we're going to add a positive number. But that positive number that we're adding is getting smaller and smaller, when we plug it, well, actually, let's look at the values. This one's a little harder to sort of analyze globally ahead of time. Let me ask this question instead. Do you agree that this sequence is bounded below? Is this sequence ever negative?
No.
No. You're plugging in a positive number in here. You're only adding. There's some fraction adding in there, but that is always positive. So you instantly know that it's bounded below by 0. Right? It's never going to go negative. And the question is it also bounded above? Let's take a look at the values here. So when you plug in the 2, so A is 2, and we do this little addition, then it goes down to 1.5. Now we take the 1.5 and we plug it in here, and it goes down to 1.416 repeating. This is bounded above by that first value, 2. These are progressively going down. So it cannot turn around and go up because we're always plugging in a smaller A sub n. If it goes from 2 to 1.5 and we plug it in there, then we're adding a small number to a smaller number than what we started with. So it's going to be going down. So this sequence is bounded. So it's bounded and it's monotonically decreasing. So we can call it a decreasing sequence. 2, 1.5, 1.4 and change, 1.4 and less change. We know that it's going down. We know it's bounded by 0. Therefore, we know the limit exists. Okay? So now the question is, how do we find the limit? and we talked a little bit about this on Tuesday, if you have a recursive sequence and you know it converges or you strongly suspect it converges, you can use that little trick that we talked about on Thursday, which is take the limit of both sides up here. You can reconceptualize this and think of this as two sequences, one on the left and one on the right. And the one on the left is this sequence, a sub n plus 1. And then on the right, you have the a sub n sequence. And you can think of them as separate sequences. So n starts at 0. So you can think of this sequence on the left as being a sub 1, comma a sub 2, comma a sub 3, etc. The sequence on the right starts at 0, so it's a sub 0, a sub 1, a sub 2, a sub 3. So these sequences are the same, except this one has one fewer terms. It's missing an a sub 0. But we all know that if a sequence converges, it doesn't matter what's happening in the front. If the tails of two sequences match, they converge to the same thing. So we are going to assume that this sequence converges to L. So if we assume that a sub n converges to L as n goes to infinity, then this sequence must also converge to L. It's the same sequence, except it's missing one point. So this will be L equals 1/2 L plus 2 over L. The limit symbol distributes into this quantity here, and then it distributes across the quantity, and then it distributes into the denominator. So the limit of a sub n, wherever it appears, is L. Now we're dealing with an algebraic equation. Multiply both sides by 2 to get rid of that. Then we have this. Subtract L from both sides. So we'll have L equals 2 over L. Multiply both sides by L. So we're going to get L squared equals 2. And then we take the square root. Now square root technically gives us plus or minus. But are these values ever negative?
No.
No. So that negative square root of 2 is an extraneous solution that doesn't have any value in this example. So that is the limit. So if you have a recursive sequence and you know it converges, you can find the limit by using this technique. And we know that this sequence converges because it's bounded and it's monotonic. So let's take a look at another one of these. So here's another sequence. We're starting at 3. Everything is positive. So we know for sure that it's bounded below, right? Bounded below by 0. And if we start looking at the values, we plug in the 3, we get the square root of 5, which is 2.2 and change. So that number went down from the 3 that it started at. So now we're plugging in a smaller number into here. So now we're going to have 4.2 and change. We take the square root of that, and we get 2.05 and change. And it's getting lower. It's getting smaller. So this is bounded below by 0, and this sequence is decreasing. Every single iteration, we're plugging in a smaller number for a sub n, so this could never turn around. And that's what I was alluding to earlier. To create a sequence that turns around, typically you have to use a piecewise defined function. So we have a sequence. It's bounded above by 3. It's certainly bounded below by 0, because this can never be negative. So we know it has a limit. If we know that a recursive sequence has a limit, then we can assume that that limit is whatever we want it to be. We'll call it L. So we're assuming that a sub n converges to L. Then we take the limit of both sides of that recursive definition. So on the left, we have the sequence a sub n plus 1. And on the right, we have the limit of the square root expression there. So I have that. All right. And then we know that the limit symbol can move through continuous functions. The square root function is a continuous function. That can move to the inside. And so that allows us to push the limit symbol to the inside, and we'll get that. We square both sides. We get that. It's a nonlinear equation. Anytime we have a nonlinear equation, we shove everything to one side and factor. So if we move everything to the left, and then we factor, and use the zero product rule, we get two possibilities, one of which is extraneous. When we look at this, positive square root's positive. So that negative number is extraneous. So that tells us that the limit is 2. That tells us that this recursive sequence has a limit value of 2. All right, what do you think? Any part of that that seems difficult? Yeah.
Could you explain the part where we got rid of the limits? How did we do that?
To here,
Yeah, before that. Yeah.
right here,
I think it was, you were right the first time.
here.
Yes.
So we have a theorem that says every bounded monotonic sequence converges. When we look at this sequence is bounded above by the 3. As soon as we plug in the 3 here, the square root of 5 is less than 3, so it's gone down. And we progressively are plugging in smaller numbers into this a sub n. So that means that our total value is always going to go down, since we're plugging in repeatedly smaller numbers. But it can never be negative. Everything in here is positive. So in our mind, we see, okay, we've got a ceiling of 3 and a floor of 0. The 0 might not be the greatest of floors. We could be upstairs, right? But 0 is definitely a floor. It cannot be negative. And so we know that this sequence is trapped in between 0 and 3. And it's monotonic. When you look here, it's progressively smaller and smaller and smaller, which means we have a bounded monotonic sequence, which means it has to converge. So every bounded monotonic sequence converges, and that the lower bound, the greatest of all the lower bounds, is going to be the limit. And so we just know automatically that, oh, well, 0 is definitely a floor, but it might not be the biggest floor. And so that's what the limit will do for us. So if we know that the limit exists, then we can take the limit of our recursive definition, and anytime we're taking the limit of an a sub n or an a sub n plus 1, we're going to replace it with L. That tells us this is the highest of all the lower bounds. It's the greatest lower bound. That's the best floor, 2. The terms are never going to hit 2, but they're going to get arbitrarily close to 2. Does that answer your question?
Yeah. How is that different from a range of a function? Is that similar?
So the range of this function is discrete. Typically when we talk about the range of a function, we're imagining some continuous curve and we're looking at the y-axis. For any sequence, when you think about a sequence, I guess it was on the prior slide, it's just a bunch of dots. So the range would be a list of numbers. So the range for this sequence is all of these individual numbers, but it's not continuous. So if you wanted to think about the range of a sequence, you can, but you'll never be able to write it down for most sequences because it's going to be an infinite number of points that can't be described in a really sort of concise way. Like when we look at y equals x squared, we can say, oh, the range goes from 0 to infinity. Bracket on the 0. open on the front on the infinity symbol. But for a sequence, because it's individual y values, you'd have to then comma list them all out. You're creating another sequence. Right? The y values would be the actual range. So yeah, so it's similar to range, but range for a sequence is discrete, not continuous. So you wouldn't get an interval. Okay, so let's see. Let's go to infinite series. So all that sequence stuff that we've just talked about, sequences are interesting for sure, but the main function of sequences is a tool to analyze infinite series. Infinite series are everywhere. Anyone that has a phone or a calculator, all the computations in there are done with infinite series. The simplest calculator is filled with infinite series, just wanting to be accessed. Let me out, let me out. So think about your calculator, think about your phone. If you type in sine of 1 degree, how does your calculator figure out sine of 1 degree? You think there's a unit circle in there with a little amoeba moving around the unit circle and figuring out the x and the y coordinate? No. What we are going to learn in chapter 11, if you look in most calc books, they mash these two chapters together. The infinite sequences, the infinite series, they get mashed together. But when we get to chapter 11, we are going to see that you can create an infinite series that is a function. And we are going to see that all of our common functions can be represented by polynomials that never end. Infinite polynomials. That's what's going to be called a power series, a series of powers of x. And that's what our calculating devices are doing. They're taking our common functions, converting them to infinite polynomials, and then there's a calculation called the error calculation or the remainder calculation, and it figures out how accurate it needs to be so that however wide your screen is, if you have 10 decimal accuracy or 100 decimal accuracy, that computation will truncate your infinite series, and then because a calculating device can figure out a polynomial value really easily when it's just multiplication, division, adding, subtracting. Those operations, those 4 operations are easy. And so we turn our common function into this polynomial approximation, but that approximation is better than your calculator's accuracy, so it works. So anytime you're typing in e to the 2, e squared, square root of 2, all of those computations are done with infinite series, which is mind-boggling because we feel like we've barely ever heard about them until Calc 2, but they are in every single computing device. Like that is revolutionary to create these infinite series that can then be used to do computations. So that's why sequences are important, because they're used to analyze these series. And everything is a series. When you get into engineering, instead of series of numbers, you have series of trig functions. So like when you think about the classic engineering example with alternating current goes this way, then it goes this way, then it goes this way, then it goes this way. And if you want to create a function that maps that electricity, there's going to be like points where it jumps and it's going the other direction. So you have points of where it's not differentiable. And so you end up with these square waves, these waves that are non-differentiable. Just from Calc 1, you know that if you have a function that's not differentiable, it's very hard to do anything with it. And so when you get into higher level math courses, you're going to turn all of these functions that are not differentiable, you turn them into infinite series of sines and cosines, then it's differentiable. Then you can do math on it, and you can do what you need to do for electricity. So you're going to start seeing all these infinite series. First here, numbers. Next chapter, series with x's. And then the next step up is series where there's all sines and cosines. And it creates you can turn a square wave into a continuous function. So you can take a derivative. So infinite series are going to be everywhere. So don't think that it's just some anomaly in Calc 2. When you get to Calc 3, Diffie-Q, we've talked about this a little bit when we did differential equations. When you solve a differential equation, you're finding a function that satisfies it. In the real world, when you get your data, the chances of it being a common function that satisfies your differential equation is probability 0. Like the idea that you're going to get e to the 2x as your solution is virtually impossible. In the real world, when you collect your data, you get your differential equation, and you go to solve it, it's an infinite series. The solution is an infinite series. The generalization of a function is an infinite series. And so we first have to get comfortable with infinite series of numbers so that we can then move on to infinite series of functions. So that's why it's so important to not shortchange the infinite series. That's why they're so important, because they're going to come back in Diffie-Q, and then they kind of go on pause until you get into engineering courses, and then they come back as Fourier, they call Fourier transforms, when you turn your function into an infinite series of sines and cosines. And super practical, very practical. So for us, we're just dealing with numbers, which is great, but it's still mind-blowing because you're adding an infinite number of them together. So, like we talked about on Tuesday, there's two sequences. There's the sequence of terms. You add your sequence of terms together to get your series. So the series is the sum of your sequence of terms. But to analyze whether this series converges or diverges, we build this other series called the sequence of partial sums. And again, the sequence of partial sums is this bootstrapping method where you keep adding one more term, one more term, one more term. So we start with the first term, then we add the first two, then we add the first three, then we add the first four. So in your mind, you should be thinking of these two sequences as very related. And we've kind of already talked about the only way your series is going to converge is if the terms are going to 0 really fast. So think of this as your sequence of terms. And if we assume the series is going to converge, those a sub n's have to go to 0 really fast. It has to be the ski slope to the lodge thing. So these have to go down really fast. And now if you want to think about the associated sequence of partial sums, you're now adding. So the first one is going to match right there. But then you add these two heights. You think about the height of those two rectangles you add, and it's going to go here. And if this sequence of partial sums is going to converge, there's going to be an asymptote across right there that it converges to. So when you're imagining a convergent series, that's what you should be seeing. You should be seeing the sequence of terms going to 0 very fast, but then the sequence of partial sums tapping out with some ceiling. There should be some ceiling that is going to be the limit of the sequence of partial sums, which will be the sum of the series. That will be the value of the series. So right here, we look at our sequence of partial sums. They're getting bigger and bigger and bigger, but they're bounded if it converges. And so if the sequence of partial sums does have a ceiling, if it has a limit, then the series converges to L. Or the value of the series is L. So we say a lot of different things about a convergent series. Any questions on the ideas that go into the description here?
I have a question.
Yeah.
So these two graphs, they are representing basically the same function, one sequence of partial sums and the other one
Sequence of terms.
sequence of terms.
So the sequence of terms is always going to be skiing down to the lodge if it converges. You got to ski fast though. It's got to be a black diamond. If it's a blue, it's probably not going to converge. You got to go fast. And then the sequence of partial sums, because you're adding. Right? This is a sub 1 is that height. A sub 2 is that height. A sub 3 is that height. A sub 4 is that height. So down here, right, you're adding these together to get all these guys. All right, so the sequence of partial sums is the collection of the first terms being added progressively one at a time.
the ceiling that we get with a partial sum, is that the same as the initial value of the sequence series?
No, because they're all positive numbers. Right, so this is a positive number, and if we're adding all these positive numbers, then the S sub n's are getting bigger and bigger and bigger and bigger, but they're getting bigger and bigger and bigger in a way that they're sort of tapering out.
And that limit equals to the limit of the other one?
The limit of this one is 0.
Okay.
The limit of it, the only way a series can converge is if the terms go to 0. So this sequence is converging to 0, and this sequence is converging to L as n goes to infinity.
Okay. And how does it relate to the last part we have if?
Here?
No, the last part.
There? This is what that says. So this says if the sequence of partial sums converges to L, then the series is L. The series converges to L, the series has value L, the series is equal to L. You can say a whole bunch of things. A lot of times we just say the series converges to L.
But, I mean, that example that we have here, and the limit for this sequence that approaches 0, right? It's not L. Is that
The sequence is going to 0, but the series is going to L. Let's look at we'll look at a specific example.
This is the summation of A sub n is L. Like
L
it's
is the summation of all the A sub n's. So if you imagine, pumping up a balloon or something, you do that first pump, then you do this pump, and the balloon is getting bigger, right? So, and eventually you're pumping in 0, and eventually the balloon is full, right? So each of those little pumping actions increases the volume of the balloon, and then wherever it stops, that's going to be the limit. Eventually you're putting in so little air that you have a finite volume. So you can think of it, in lots of visual ways. But this has to keep getting bigger because you're still putting in more and more and more and more. You can think of it as a bowl and you're pouring in water. You pour in a cup of water, then you pour in half a cup of water, then you pour a third of a cup of water. So it's getting bigger, and it's going to overflow unless these get close to 0 really quickly, which is what we did with the improper integration. We saw that we had to have that curve go down to 0 really fast. 1 over x was not fast enough. That caused divergence. But 1 over x squared was fast enough. So these guys have to go to 0 really quickly in order for these guys to have a ceiling. If these guys don't go to 0 fast, then this is just going to grow without bound, and you're going to have a divergent series. That makes sense? So let's look at the geometric series is a pretty good example. So the geometric series is the one that's the most intuitive. It's that repeated multiplication by the base. 2 to the, whatever the exponent is we're using, k in this case. Like 2 to the k means multiplying 2 by itself infinite number of times. Obviously going to go to infinity. 1/2 to the k obviously is going to go to 0. What's fascinating about the geometric series is this. So we are going to get convergence if the magnitude of r is under 1. If that magnitude is under 1, so in other words, r is some number in between -1 and 1, the geometric series will converge. Otherwise, if it's bigger than 1 in either direction, magnitude bigger than 1, diverge. Okay, so we know that. The question is, what does it converge to? And look at this. Look at this. That is like the simplest looking answer. A over 1 minus r. Infinite series that we can consolidate down to some basic formula. A divided by 1 minus r. That's like a simple formula. Why is that possible? Let's check. So here is our geometric series. Geometric series, we start, often with geometric series, we start with k equals 0. You can start it with 1, but for the formula's sake, it's easier if you start with 0. So our geometric series is starting at 0. We plug in 0 into this AR to the K formula. That's what it looks like expanded. So there's the expansion of our geometric series. If you wanted to, you could say, and I know a lot of people love to factor constants out, that A is a constant, you could write it this way also. You could factor the A out. And so the infinite series part is right there with just your it's called a common ratio, that common ratio of R. Okay, so let's look at S sub n. S sub n is the sum of the first n terms. If the counting starts at 0, the nth term will be when k is equal to n minus 1, because we shifted it all. If we were counting starting at 1, 1, 2, 3, up to n, here we go. But if we start at 0, we have to shift everything 1 unit to the left. So instead of starting at 1, we're starting at 0. Instead of finishing at n, we're going to finish at n minus 1. Right? So if we have 5 terms here and we shift here, here we count 1, 2, 3, 4, 5. Here we count 0, 1, 2, 3, 4. So it's just shifted 1 unit. Now they do this clever process, multiply by r. All right, we know how to multiply by r. Now let's combine, let's take this and subtract off this r sub n. So we're going to do this row minus this row. Well, there's a ton of cancellation, right? That cancels with that cancels. All this stuff cancels. The only two things that don't cancel are those. So if we subtract the two, S sub n minus r, S sub n, we get a minus ar to the n. On the left, factor out the S sub n. If you factor S sub n to the front, you have a 1 minus r. Divide both sides by 1 minus r. This is S sub n in closed form. Right? There's no infinite thing happening anymore. There's no dots anymore. It's just a closed formula. And if we choose an r value that's under 1 in magnitude, less than 1 in magnitude, we know r to the n goes to 0. Right? If r is between -1 and 1, and you raise it to n, that's going to go to 0. So the only thing that's left then, if this part up here is going to 0, that part right there is going to 0, all that we're left with is the a in front and the 1 minus r. That is the sum of your infinite geometric series. Series. So that is very nice. We have a super easy way with the geometric series, which are very common, to find the actual sum of the series. All right, let's go ahead and take our 10-minute break, and then we'll look at some examples of geometric series and try to put some specific examples into play. Let's take a break. With the geometric series. So I'm just choosing an r value in this example of 2. Now before we look at the specifics here, we're just trying to get some of the terminology stuff down, get some of the formula stuff down. If we have a geometric series with an r value of 2, does it converge or diverge? Geometric series with an r value of 2. So you have 2 to the k. It's got to diverge, right? The r is bigger than 1. 2 times 2 times 2 times 2 times 2. It's going to go to infinity. So we know it's going to diverge. And there's what the series looks like. So we've got our series, 2 to the k, 2 to the 0 is here, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4. Obviously it's going to diverge. Those terms aren't going to 0 fast. They're not going to 0 at all. If they're not going to 0 at all, diverges instantly. These terms would have to go to 0. If you're blowing up the balloon, in your mind it's going to explode in your face. And not too far down the line because these are getting big fast. So, A represents the first term in the series. So that's A. A is 1. It's always the first term if you have it in expanded form. R is 2. We have a series that has a base of 2. The S sub n formula, this tells us a formula for the nth partial sum. And in this case, the geometric series is one of the few series and only one of two series that we are going to look at where you can get a formula for S of n. 90% of the time, you cannot get a formula for S of n. If you can get a formula for S of n, it's easy, because then you just take the limit. And we know how to take limits. But 90% of the time, we can't get an S of n, which is why we're going to have to learn all those convergence tests later on. So when you have a geometric series, you're psyched because you can get the S of n. So there's S of n for this series. If we plug in 1, right there, we get 2 minus 1, so S sub 1 is 1. If we plug in 2, we get 4 minus 1, which is 3. That's the sum of the first two terms. S sub 3 is the first 3 terms, but here's a formula for it. So if we plug in a 3, we get 8 minus 1, which is 7. S sub 4, we plug in a 4 there, we get 16 minus 1, which is 15. So that's the sum of the first 4 terms. So we have a formula for S of n. And then we take the limit of S of n, and clearly that limit is infinity. Right? As n goes to infinity, 2 to the n minus 1 goes to infinity. It's infinite. So that means the series diverges. Just because the series diverges doesn't mean that you can't come up with a formula for S sub n. So this will tell us S sub 100 if we wanted. S sub 100 would be 2 to the 100 minus 1. So we could find S sub n. Here is a picture of the sequence of partial sums. Clearly not converging. Right? The sequence of partial sums, you should be seeing it tapering off and having a ceiling if it's going to converge. 1.9, 1.99, 1.999, etc. This is going to infinity. So therefore, the series diverges. So we have to be careful here. Let's take a look, especially with the geometric series, because 99% of the time with the geometric series, we are starting with 0, not 1. Because it's just easier with the formulas. So S sub 1 is 1. That's A sub 0. So in this case, S sub 1 is A sub 0. Okay, that's the first term, is A sub 0. S sub 2 is A sub 0 plus A sub 1. So just be aware that the index of how these indices work, even though this series starts with 0, we still consider that the first term, and so S sub 1 is going to be A sub 0. So you just have to be careful with your counting.
Do you ever start with an S sub 0, like at all?
No. Because the meaning of S sub n is that it's the sum of the first n terms. So S sub 1 means the sum of the first term. So S sub 0 would be the sum of no terms. So we don't use an S sub 0. We use an A sub 0 just as a counting mechanism, because it's going to make this formula here and the A over 1 minus R, which we'll see in a minute, it just makes those formulas work if you can start at 0. So let's take a look at this. Okay. These, yeah, Sebastian.
On the previous one, wouldn't for when you plug the A and the R on the equation S of n, wouldn't it be negative 2n plus 1?
Say that once again, plugging into here.
Yeah. I'm just confused how you got to the 2n minus 1, because I'm looking right at it.
What is 1 minus 2?
They're just negative 1.
And then if you divide negative 1 into the numerator, you get positive 2 to the n and negative 1.
Okay, gotcha. Never mind.
You see it?
Yeah.
Yeah, so if you divide by negative 1, the effect is that it's just reversing the order of that subtraction up top. Everyone agree with that? Yeah. Yeah, once you see it, it's like, okay, I get it. All right, so with this example here, so S sub n can be used to find the sum of a finite series. So these are clearly finite because they don't go to infinity. So we're going to look at, all three of these are finite. Can you tell me how many terms are in that first one, number 12? How many terms are in there? How many?
9.
Okay, I hear a 9. Let's do one that's a little simpler for a second. No, we can do this one. Let's write this one out. There's not so many terms that we can't write them out. So I heard 9. So the first term is going to be 2 to the 4. And then the next term is going to be 2 to the 5. I'm just going to write these down. Normally I wouldn't write them all down, but we're counting here. So let's make sure we understand how to count. So those are all the terms. Everybody agree those are the terms? How many? 1, 2, 3, 4, 5, 6, 7, 8, 9. The common mistake is to say 8. 12 minus 4. But you have to remember that the 4 counts. So you can do 12 minus 4, but then you have to add 1. So that's one way to do it. So this one would have how many terms down here? So 6 minus 0 plus 1, so 7 terms. If you start counting at 0, 0, 1, 2, 3, 4, 5, 6 is 7 terms. So that's one way to do it, is upper minus lower, add 1. Another way to do it in your mind, if we started at 1, if we went from 1 to 5, how many terms would there be? If you went from 1 to 5? 5. If you start at 1, then the upper number is exactly how many terms there are. So you could think in your mind, what do you do to this 4 to get to 1?
3.
Subtract 3. So then you could subtract 3 from the 12 and get 9. So there's a couple of ways to get the number of terms. So if we want the number, if we want the total of this, if we want to add all that up, that looks pretty brutal to add all that up, but we have our formula right above it. What should this be? S sub, how many terms are there?
9.
9. So we want to add all 9 terms up. S sub 9. That adds the first 9 terms up. A. What is the A value? A is always the value of the first term. So in this case, A is 16. It's the first term. And then we multiply by 1 minus R, and R in this case is 2, raised to the N. N is matching this over here, so it's 2 to the 9, all divided by 1 minus R. So this turns into 16 times 2 to the N minus 1, 2 to the 9 minus 1. This is negative 1 downstairs. If we distribute it to the top, we just flip the subtraction. So that's what that all adds up to. Now, whatever 2 to the 9 is, we can type it in the calculator, subtract 1 and multiply by 16 and get the number. But that's how we can do that fast. Let me just show you something in Desmos, which is pretty slick. So Desmos is an amazing tool to check your work or to do analysis of all sorts of things. So we can do this straight in Desmos also. We just type sum. We're going to go from 4 to 12, and then if we just put in 2 to the to the N, they use N. There it is. 8176. So Desmos can check all of these summations pretty easily for you. So 8176. So that is the, so obviously if you don't go to infinity, you have a finite series, so it's going to have a sum. If you went to infinity, then it would say it does not exist. It becomes infinite. But if it's finite, then you can do it. Okay. Now let's take a look at this one. So you all try this one. So find the sum of this one, number 14.
So as we only use, or if we can use the equation as of n when it's not going towards infinity. But if it's going on a definite one, just like from here to here,
Yeah.
then in that case, you can use this.
And if it's going to infinity, then we're going to use the other formula. If it's going to infinity, we're going to use the S equals A over 1 minus R. If it's going to infinity. So
And A will be representing
A always represents the first term.
the first term.
First term.
Eres tonto.
All right, so let's see if you can come up with your S.
¿Qué es pi al 6?
I'll write out the terms here.
Sí, no sé cuántos son. No, no, es pi a la 6.
¿Qué estoy haciendo?
Sí, no es por ciento, es a la 6.
Yeah.
Ahí está copiando el problema.
Hacemos 1 sobre pi al negativo 6. ¿Ves?
Sí, pues está bien. Así es.
Ay, pero ¿qué hizo?
Pues solo puso arriba 0, 1, 2, 3.
¿Qué estoy haciendo?
Más pi a la 1. Más pi.
Eso no.
Ay, sí,
So what's this one going to be? S sub what? S sub, how many terms?
Ah, estás calculándolos
S sub
ahorita.
7.
Es una locura, usa la calculadora.
So this
Pi a
series
la 1 es pi.
has 7 terms, and we want to add all 7 of those terms together. So we're going to treat it as S sub 7.
No, yo sí.
So that formula up there, what's the first term?
1.
1. Pi to the 0 is 1. So that A out in front is a 1. So A is equal to 1. So then the numerator, what is the R value?
Pi.
Pi. That's the common multiplier. So we're going to multiply by pi repeatedly, so that's our common multiplier. So 1 minus pi in the bottom, and in the top, 1 minus pi, but there's an exponent on the pi, and that exponent is
7.
7. So there is the sum of the series.
Ah, porque es la suma.
And now, we never approximate unless we're asked to. So that is what S sub 7 is. That's the sum of this series, this finite series. Unless it says to round, we would just leave it like that. The only time we round is if the instructions say find an approximation. So this is an exact answer.
And what if we were to approximate? How would that look like?
So then we would have to type it into whatever our approximating tool is.
It's like 1410.
14.1?
No, well, 1,400.
Oh, okay. I'm gonna type it in here just to see. So it's 1 minus pi, was it to the 7?
Ya
Yeah.
veo, ya veo.
Whoops, that didn't go up. And then divided by 1 minus pi. So that would be our approximation. Yeah, but we only are going to do that if we're asked to. Your default should always be to find exact answers. That should be your default. All right, let's try this last one on here. How many terms does this last one have?
47.
So 50 minus 4 plus 1, or subtract 3, subtract 3. Whatever is the most intuitive way for you, 47. So we're going to find S sub 47. We are not going to write out these terms. So this is A. A is first. A is always the very first term. The very first term is found by plugging in the very first first index value, 4. So this is A. E divided by pi raised to the 4th power. That's A. What is R in this case?
E over pi.
So A, I'm gonna just write these separately over here just to make sure that we have them both. So everybody agree that E over pi, that common multiplier, E over pi, it's gonna get multiplied by itself again and again and again and again and again for a long, long time. Not forever in this case, but for a long time. So then we do 1 minus r in both the numerator and denominator. But the 1 minus r in the numerator, we have to do a little extra business here, and we have to put a 47 up there. So that is the sum of that finite geometric series. Now that is not simplified. If we are trying to simplify this, let's just do a little bit of algebra here to make sure that I guess to practice a little algebra. So this is 1 minus e to the 47 over pi to the 47. 1 minus e over pi. What can we multiply top and bottom by here to clear the fractions out in one fell swoop?
Pi to the 47.
Pi to the 47. We multiply top and bottom by pi to the 47, so we're multiplying by 1 once again. We love multiplying by 1. So e to the 4 over pi to the 4 multiplied by, this is going to be pi to the 47 minus e to the 47, all divided by pi to the 47 minus e times pi to the 46. Now, often, if we are going to factor something to the front as a multiplier, we want to factor the entire common factor out. There's no other common factor in the numerator, but in the denominator there's a common factor of e to the 46. So the simplified answer would be to factor out that pi to the 46. Factor out that pi to the 46. And so we leave nothing, we don't do anything in the numerator here. But in the denominator, we want the greatest common factor pulled to the front, so we're going to pull that pi to the 46, and we're going to be left with pi minus e. So that would be our simplified answer. And then if they asked us for an approximation, we just type that into the calculator and go. But it didn't. Or did it? It did. Well, you can type that in and get the approximation. That's not hard. Okay. Let's look at how much easier it is when the series is actually infinite. It's way easier. Look at our formula. So when we take a look at this first one, A is 1, R is 1/4. So A is the very first term. A is found by plugging in the first index value. So we end up with 1/4. That doesn't look like a good 1/4. So the sum of this infinite series is going to be so much easier to find. Done. We just added an infinite number of numbers together. One divided by 1 minus a quarter. 1 minus a quarter is 3/4. We flip the 3/4 and get 4/3. That is the sum of that infinite series. Much easier than the partial sums. All right. Let's take a look at this one. What is A and what is R?
1 over pi.
All right, 1 is the first term, so A is always you just look at it, it's the first term. If it's expanded, if it's not expanded, you plug in that first index value and figure out what you're going to get. And then R is the common multiplier. It tells you how to get to the next term. So then the S here, the sum of this infinite series is 1 over 1 minus 1 over pi. If you multiply top and bottom by pi, you'll clear the fraction. So multiply by 1, we'll end up with pi over pi minus 1. So that is the sum of that infinite series. It's way easier to use an infinite series than a finite series. Okay, think to yourself about the two questions here. So just think in your mind, what is A, what is R? Those are the two things we need. Our formula is A over 1 minus R. So we need A and we need R. Think to yourself what A is and what R is. Maybe I'm going to move those down below because we might want to expand this series a little bit just to make sure. All right. What is A? A is, did you say it, Brandon? What? So A, we plug in the 2. So what is it? Did you say 5/4? Good. Very good. 5/4. So A is the first term, which means plug in the first index value, and that's 2 to the 2. 2 to the 2 is 4. So that very first term is going to be 5/4. That's going to be our A value. Now, how about R? What do we think R is?
1/2.
Yes. If it's not obvious, write out your first few terms because then it will be obvious. So let's write out the first few terms. Okay, so plugging in the 2 is going to give us 2 squared down here. The next term, notice there's no m in the numerator. So there's a 5, and then it will be 2 cubed. And then it's going to be 5 again, and it's going to be 2 to the 4th, plus etc. Right? So the common multiplier, we are going to do repeated multiplication by 1/2. So we're multiplying by 1/2 again and again and again. So that 5 is a little misleading, a little bit of a distraction. That 5 is going to be the numerator no matter what. So when we multiply that 5, because there's no m attached to it, so it would be totally different if we had this. If we had this series, 5 over 2 quantity to the m, let's suppose m started at, let's not start at 1. Let's say it started at 2, went to infinity. Tell me what A is first in this case. 25/4?
Yeah.
So A is the first term, and R in this case is going to be 5/2. Here, because the m is an exponent on both, you have a repeated multiplication of 5 over 2. Whereas this case, this example, we just have a 1/2. So our series will add up to A, which is 5/4, multiplied by 1 minus R, both numerator and denominator. Oh, nope. This is a full series, so A, I want to write this differently. Shoot. It's just A over 1 minus R. So A 5/4 over 1 minus R. So the denominator is 1 minus 1/2, which is 1/2. Dividing by 1/2 is multiplication by 2. So 5/4 times 2 is 5/2. Sebastian?
Could you also factor out the 5 outside of the equation
Yes.
as well, since it is like going at infinity?
Mm-hmm. So you could do that. You could write this as 5 summation, and you could write this as 1 over 2 to the m, like that if you wanted to also. And so that would be totally equivalent. So you could find the sum of this, and then multiply by 5. Mm-hmm. That would also work. Okay, now this one here is given to us in expanded form. Oh, it's not gonna let me move that? Come on. So can you identify A?
116.
So A is always first term of the series, so if it's expanded, it's literally the first number we're staring at there, 116. Now R. R is the common multiplier. So we have to figure out how do we get to the next term. We're not even 100% sure this is geometric until we look a little more carefully. So let's take a look. So what are we multiplying to get to the second term from that first term?
3/4.
3/4. So we multiply by 3/4. Okay. That checks. 3 by 1 is 3. 4 by 16 is 64. Now for this to be geometric, these guys better do the same thing. So let's check. We multiply that by 3/4. 3 times 3 is 9. 4 times 64 is 256. That's right. And then here, same thing. 9 by 3 is 27. 256 multiplied by 4 is 512 multiplied by 2, which is 1024. So yes, totally agree. So this is 3/4. So once we have the A identified and the R identified, then we're golden. The sum of the series is going to be A, which is 1/16, divided by 1 minus R. And there's lots of ways to simplify this. I feel like it's really helpful to get into this habit of multiplying by 1. It helps you do things pretty fast. It helps you practice your arithmetic. Look at that. That is the sum of that infinite geometric series. Any questions on any of those geometric series examples?
When you factor out the m instead of the 5/2m, I know that
You said factor out the m,
when you did the Riemann sums, the exponential,
this piece,
yeah,
factored out the 5.
right. But
Okay.
then the m, you factor out the m outside of the.
Oh, I understand, yeah. So this could be 1/2 to the m, or 1/2, those are the same. So you could write it like this also. You could say this is m equals 2 to infinity of 1/2 to the m. It's not as obvious what r is though. So when you pull the m to the outside like that, then you can see the r a little more clearly. If we look at the generic form of a geometric series, usually they are going to write it in this arc form. So r is raised to a power. So r is, so the exponent is, on the outside. So when you are looking in practice here, you can see that r is going to be 1/2, but it's not necessarily obvious from there or there that r is 1/2. But you could either rewrite it so that it's in that r to the k form, or you could do this expansion to make sure you're 100% sure what that common multiplier is. So let's. All right, so you all try the first one, 23. So that's an infinite series. Notice that the common ratio is negative. Shouldn't matter though. We have our formula, it doesn't change, a over 1 minus r. How about A?
1.
Everyone agree? So raising to the 0 power, anything to the 0 power is 1.
But it's negative, so doesn't that make it -1?
No, because this negative is on the inside, right? That negative is on the inside, so it's affected by that exponent. So negative 9/10 raised to the 1 would be negative 9/10. Negative 9/10 raised to the 2 would be positive 81 over 100. So because the negative's on the inside, if you raise it to the 0, the whole thing becomes 1. So it's only if that negative were on the outside that it wouldn't be affected by the exponent. So that is going to be 1 total. So if we had that situation where the negative was not included, you could factor the negative out to the front if you wanted. But in this case, since it's trapped inside the parentheses, it's included with that exponent, so 1. And how about r? Negative 9/10. Exactly. So whatever we see that's below that exponent. So our sum is not so hard, right? It's just going to be 1 divided by 1 minus 9/10. And if you multiply by 10 over 10, you're going to end up with 10 divided by, 10 goes here and it cancels that out. Over here you get 10 plus 9, so you get 10/19. That'll be the sum. Now, if you're ever not sure what the A and the R is just by looking at that summation form, write out the first few terms, expand it, and usually it becomes clear. So when we look at this one's a little convoluted. Certainly you can find A pretty easily because you plug in that first index value. So A is going to be negative E parentheses to the negative 1. So that's going to be negative 1 over E. Negative 1 ETH. So that's A. R, got to be a little careful here. So our generic form for a geometric series is this arc form. So here is our standard form, A r to the k. This k has a negative 1 in front of it. So is there a way we can pull that negative 1 away from the k? Is there a way we can rewrite this so that we...
1 over negative E is in the parentheses.
1 over negative E
And then
to the k.
is in the parentheses.
Does everyone agree? So a negative exponent has the effect of flipping the fraction. So we can treat this, recall that if you have a to the negative 1 is 1 over a. So if you have something like a to the minus k, you could write that as a to the negative 1 to the k, which is 1 over a quantity to the k. So you can remember the power to power multiply thing. If you have power to power, they multiply. So if you wanted to pull a coefficient off, you could pull off that coefficient of negative 1. So that said, R is equal to negative 1 over E, correct? It's equal to the same thing as A. So that tells us that our sum is A, which is negative 1 over E, divided by 1 minus 1 over E. Let's multiply top and bottom by E. That'll be a quick and dirty way to get rid of the fractions. So that'll be our that'll be our exact sum. The exact value of the series. It'll be the limit of the series. Any questions on that? Finding the R, finding the A. If you're ever not 100% sure what they are, just write out some terms. So you could plug in 1, plug in 2, plug in 3, and just see what the pattern is. If it's not obvious from the summation notation, write out some terms. You can find your R easier that way.
Excuse me,
Yeah?
so does it mean that the result is negative?
Yes.
So it can be negative?
Can be negative, for sure. Yep. Yeah, if you're adding up a bunch of negative numbers, it could be negative. Or, in this case, is every term negative or just some terms? Just some, right? When the k is an even number, the term is going to be positive. When k is an odd number, the term is going to be negative. How about the very first term? Is it negative or positive? Negative. That term dominates. That's the biggest term in magnitude. Because all the terms are getting smaller. Right? So k starts to the first power, and then when it goes to the second power, we have an e squared in the denominator. That's smaller in magnitude. So if you have a series that's alternating, whatever the sign of the very first term is, that's going to dominate, and you're going to end up with a sign that's equal to whatever the sign of the first term is. So because this first term was negative, that's going to be that's the biggest term in magnitude. And because it's negative, that's going to dominate and end up with a negative answer. Yeah. Good observation. Okay, so last slide with this stuff. We have these repeating decimals. These are hidden geometric series. A repeating decimal is a geometric series. Let's try to figure out how to write it as a geometric series. So we're going to peel off chunks of this decimal and write it in a slightly different way. So first, let me just do it decimally. Let me do it like that first. Does everybody agree with that?
Yes.
So this first one you could write as 37 over what? Power of 10. 1,000? All right, if you divide by 1,000, you're going to move that decimal 3 to the left from the 37. And 37 will become 0.037. Okay. This one, we're going to have 37 over, and I'm going to write this as 10 to the 3 because the numbers are going to get kind of big. What is this one going to be? 10 to the 6. Yeah. And that's going to continue on. So we've now written it as a geometric series. And let's put in that third term just to make sure we're sort of on track. This is going to be 37 over 10 to the 9. So these are going to be 3 apart because we have a 3-digit pattern. So we have a 10 to the 3, 10 to the 6, 10 to the 9. What is A?
37 over 10 to the 3.
37 over 10 to the 3. How about R?
1 over 10 to the 3.
1 over 10 to the 3. So S is going to equal A, 37 over 10 to the 3, divided by 1 minus R. And if we multiply top and bottom by 10 to the 3, we get 37. This is a 1. This is 10 to the 3, which is 1,000. 1,000 minus 1 is 999. So there is the calculus way to find that rational, to write that rational number as a ratio of integers. So that's the calculus way to do it. I think we talked about the algebra way to do it earlier this semester. Did we? Let's do one at least with the algebra way just in case you, I'm pretty sure, feel like we did it, but
It
no.
was like a crash course.
How would we do this with algebra? So if you're in algebra 1 or 2, this is how you would do it. Does anyone remember?
1 plus involved.
No. There is a letter involved. What letter comes to mind when you think of algebra? X. So there is an X involved. So if we write X as this thing,
You multiply both sides by 1,000.
multiply both sides by 1,000 so that we sort of peel out the pattern. So if we multiply by 1,000, then we have 37.037037 repeating. And then on the right-hand side here, we turn it into addition, so it's 37 plus what?
X.
X, right? This part right here is that part right there. That's X. So then we have the X. Then we subtract X to the other side. And we get the same exact number, of course. So that's the algebra way. The algebra way. Calculus way is a little more elegant, using your geometric series prowess. Okay, how about this one? Let's first write it as, so we have this repeating, 2-digit repeating thing. So I'm going to rewrite this as 1 plus 25 over 100 plus 25 over, let's see, so we did that part,
10,000.
so then it's going to be over 10,000. It's going to be 100 times 100, 10,000, plus etc. So this is going to be equal to 1 plus, we didn't write this one as a summation. Let's write this one as a summation just for practice. So this is going to be 25 divided by 10 to the, is there a way that you can think of writing this if we wanted to write it as a summation here? So K is going to go from, well, let's make this, I'll let you. So what did you say, 2K?
2K.
So if we start at 1, that will be 2K for that. We're going to agree? And if we go to 2, it's going to be 10 to the 4, which is that. So that's how we could write this in summation notation. Maybe we should write this one in summation notation also just for practice. So this one would be sum. Here we're going to have 37 divided by 10 to the, so how could we, what can we put up there? 3. So if K is going to go from 1 to infinity, what's that going to be? 10 to the, 10 to the what? 3K? Yeah? 10 to the 3K. So you could write it like that? So that would be the summation form. When K is 1, you're going to get this term. When K is 2, you're going to get that. When K is 3, you're going to get that. And then you could do some rewriting in there too. What is, could you peel off that, that 3? Yes, you can. What is it going to give you in the denominator? What's the denominator going to be if you combine the 3 and the 10?
Oh, 100.
Close.
Or sorry, 1,000, yeah.
But that's the idea. If you have a product in the exponent position, you can implement one of them as an exponent first and then the other one second. So then here you can see that A is going to be 37 over 1,000, and your R value, the 37 doesn't count because there's no exponent on it, but the R value would be 1 over 1,000. Repeated multiplication by 1 over 1,000. So down here, We've got that. Let's do the same type of thing here. So we have 1 out in front. And that's going to be k equals 1 to infinity. Let's make this 25 over 100 to the k. And if you wanted to write it in that arc form, we could go even further and write this as 25, that's the a, and then the r would be 100th to the k. That would be that standard geometric series form where we have a r to the k, the arc form. So, the sum is going to be 1 plus, so we've got the 1 in front, and then we have our infinite series part, and for this infinite series part we have to identify a and r. A is the very first term. What's the first term going to be there? So you plug in the 1, we get 1/4. Good. And then the r part's whatever's below the k. So this is going to be 1 plus a over 1 minus r. So we have that. Multiply top and bottom by 100 would be the easiest way to clear out the fractions, or at least a way to clear out the fractions. So then we're going to have 25 in the top, and then we're going to have 100 minus 1 in the bottom. So we're going to have 1 plus 25 over 99. So we're going to write the 1 as 99 over 99. $124 over 99. So this will be the sum of our geometric series. Yeah. All right, questions on that? Is there any algebra stuff you're sort of struggling with on that you want to talk about? So the main thing is knowing your rules for exponents. That we've seen actually a few times so far. So laws of exponents are important. All right. So telescoping series are the one other series in this class where we are going to be able to find S sub n. S sub n is great if you can find it, because then you just take the limit of S sub n. The only two series that we can do this for are geometric and this new one that's called telescoping. So let's take a look at what it means for a series to be telescoping. So S sub n, if we can find it, is amazing. Let's take a look at the terms of this series. So if we plug in a 1, we get a third minus a fourth. I'm going to leave it in parentheses. So that's the first term. Second term, we plug in a 2, and we get a fourth minus a fifth. So let me put the k values down here. So I plugged in a 1, then plugged in a 2. Now we're going to plug in a 3. Plugging in a 3, we get a fifth minus a sixth. And this goes on forever and ever and ever and ever and ever and ever. And it feels like the sum might add up to a third. That seems very plausible with this one. So it's called telescoping because we have this cancellation pattern where we get a whole bunch of stuff that just cancels. It's kind of like a telescope collapsing. Okay, so our hunch may be that the sum is 1/3. But we need to prove that. And to prove the sum of a series, we need to take the limit of S sub n. So we need to figure out what S sub n is. S sub n is the sum of the first n terms. This one is nice because it starts at 1. That means the nth term is going to be when k is n, because it starts at 1. So S sub n is going to be all that stuff. So 1/3 minus 1/4, all that stuff. And usually we'll put 3 terms in the front and 2 in the back. So this is the first term, the second term, the third term. And we know that we have to go all the way down to the nth term, and the term before the nth term is the n minus first term. So we'll put 2 terms in the back. So, and starting at 1 is nice because then we end at n. That's the simplest context. If it started at 0, we'd have to end at n minus 1. If it started at 3, then we'd have to end at n plus 2. So, let's plug in n minus 1. So that's our k value. These are the k values in red. So we're plugging in a k value of n minus 1. So when we plug in n minus 1 there, n minus 1 plus 2 is going to give us n plus 1. So 1 over n plus 1 minus, plug in the n minus 1 here, we're going to get 1 over n plus 2. Plus the nth term, we just plug in an n. So we're going to get 1 over n plus 2 minus 1 over n plus 3. So that, bless you.
Thank you.
That is S sub n. Looks terrible, but it's going to collapse. So we start looking at the collapsing mechanism like we already saw. Those cancel, these cancel, and then this 1/6 is going to cancel with something in the middle here. Now we have to figure out going the other direction too. We need to get a nice formula for S sub n that we can then take the limit of. So when we're going to the right, it's the second part of this term canceling with the first part of the next term. So going to the right, seconds cancel with first. Second cancels with first. Second cancels with first. If we change our perspective and we go to the left, if we start right here and go to the left, it's this second part that cancels with the, excuse me, it's this first part that cancels with the second part of the prior. So if we're going to the left, it's the first that cancels with the second of the prior. So going to the left, the first in this term, the first cancels with the second of the prior. So that means this first in this term must cancel with the second of the prior that's somewhere in those dots. So there's only 2 terms that remain. This and this. So that tells us that S sub n is 1/3 minus 1 divided by n plus 3. So this is the formula for S sub n. And that's what we're looking for. Whenever possible, we want to find S sub n. And a telescoping series is the only other series that we're going to look at where S sub n can in fact be found. That's great. What do we do with S sub n? If we want to find the sum of the series, we take the limit of S sub n. So S, if it exists, will be the limit as n goes to infinity of S sub n, which tells us S is going to be the limit as n goes to infinity of that amount, 1/3 minus 1 over n plus 3, and that is 1/3, which was what our hunch was originally. So that is the sum of the series. Now, not all telescoping series are going to be so easy that you can just look at the first number. They're going to get more complicated. So the process, though, is revealed in this easier one. We need to come up with S sub n, and then we take the limit. And often the sum of the series is going to be, something to do with the first few terms. But you need to be able to find S sub n.
Is the way that you cancel the ones that are just gonna cancel against each other, the way that you cancel it, is it gonna matter for the ones when you're canceling the ones with the n?
Yes. So we kind of established the pattern in front, which is obvious. It's like, oh, that with that, that with that. But then we want to look here and figure out, well, if we go the other direction, what's happening? So when we're going to the right, it's second with first, second with first, second with first. When we're going this way, it's first with second, first with second. So when we come down here, it's the first with the second, it's the first with the second. So we kind of use the leading terms to get the pattern down, and then we apply it to the end and figure out. The hard part is figuring out, well, what's still left over here? And so we need to be able to get this S sub n. Taking the limit of it's pretty easy, but we need to be able to get that formula for S sub n. And remember that S sub n is always the sum of the first n terms. Always. So if this starts at 0, then this ends at n minus 1. If this starts at 2, this ends at n plus 1. We just have to shift so that we have exactly n terms, not n plus 1 terms, not n minus 1 terms. We have to have exactly n terms. So if this one starts at 3, the end is going to be n plus, no, 2. Think of it this way. If this starts at 3, we added 2 to this. So then we would have to add 2 to this and get n plus 2. So if it starts at 3, the nth term will be for a k equal to n plus 2. Right, if you add 2 to this, you get 3. 4, 5, blah, 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 add 2 to this and get n plus 2.
Wait, is the n the index?
Yes. Well, yeah. It's the index. Yep. The index. Okay, so let's stop there. Is it time? Is it time? Yeah. All right, let's stop there. Oh, we still have 30 seconds.
No, we do not.
Oh, we
Clock is
don't.
fast.
I'll give it back to you during the test.
Better.
It's actually only 15 seconds. I'll hand it back to you. With interest. I'll give you an extra minute. Yeah, absolutely.
Why are we going with 1 over n plus 3? Wouldn't there be something like...
Because, so S sub n is finite.
Okay.
So it's true that the infinite series goes on forever, but anytime we want to analyze an infinite series, we figure out what S sub n is equal to and then take its limit. So S sub n is finite. And it's going to mean, like S sub 1 is the first term, S sub 2 is these terms, S sub 3 is those. So S sub n is the sum of the first n. And if k starts at 1, then it's nice and easy because the nth term is going to be when k is n. The trickier thing is if it doesn't start at 1, in this case it starts at 3. So a sub 3 will be the first term. And then to get to the nth term, this is 2 more than that, so we'd have to go 2 more than that. Does that make sense? You can think of it this way. If we have, the k values go 1, 2, 3, and then n minus 1, and n plus 1. So this is what you would keep plugging in. This is the sum of the first n terms if you start at 1. If you started at 2, this would be the sum of the first n terms. And if you started at 3, this would be the sum of the first n terms.
I saw him in engineering.
Does that make sense? Yeah. Because we always want to add, we're adding n terms. Like let's just say n is 10. So if we're adding 10 terms, we might go, so there's 10 terms. But if we start with 2 to add 10 terms, we'd have to go to 11. If we start with 3 to to add n terms, we have to go to 12.
help center.
So that's the shifting idea that we want to
Did you see the lab, the friction lab?
really interpret this S sub n as the sum of the first n terms, not the sum up till k equals n necessarily,
No?
but the sum of the first n terms.
Oh, brother. We had to define the static.
Question, Sebastian?
Where
It was on
X distance away from our.
Part 5 where they looked at series or geometries, geometry.
Geometric series?
Yes.
Figure out what-
It's the one where there's the rim